Hi guys, hope you all are doing well, and in case you haven't subscribed my channel yet, just make sure that you subscribe the channel and hit the bell icon so that you can get the notification as early as possible. Uh, Today we are continuing with our topic of kinetic theory of gases, and we are supposed to do ratio of specific heats today. You won't be able to follow this topic in case if you do not know degrees of freedom and constraints and law of equipartition of energy. So in case you have not followed, or if you haven't followed my previous videos, then I would request that you kindly go to the playlist and just try to do few videos, just like last 3 to 4 videos before this video, and you will be able to follow this thing. So today we are going to start with ratio of specific heat, and if you can see, ratio of specific heat is written as gamma. This is called as gamma, and gamma is nothing but ratio of specific heat, that is Cp upon Cv. Now what is this Cp? Now Cp is molar specific heat at constant pressure, and Cv is same, molar specific heat at a constant volume. So Cp and Cv is molar specific heat at a constant pressure and constant volume. Yes, this video is not in the scope of what molar specific heat of at constant pressure and volume is. Maybe in your previous grades you might have studied about that, and this is what it is. Now what we are going to do is we are going to start with something called as monoatomic gases. Then in the video we might come across diatomic gases and also polyatomic gases, but probably the video is going to be long with one itself. Like for monoatomic gas the video is going to be long, so maybe diatomic and polyatomic I will be discussing in another video. Now for monoatomic gas, if this is the atom, like kind of a helium is basically a monoatomic gas. So its single atom is its own molecule, it's not going to share any other atom, and its molecule and atom is one and the same. So if this is the helium atom, or maybe any monoatomic gas which has a single atom as its own molecule, it can move in the x direction, it can move in the y direction, and it can move in the z direction too. However, it will have three translational degrees of freedom, as it is moving in three possible directions, but rotational degrees of freedom and vibrational degrees of freedom will be absent here, as vibration will only come when there is a bond between two atoms, and rotational will only come when there is a moment of inertia, and moment of inertia would be absent for a single atom molecule. So if you see kinetic energy per unit molecule, which I have already derived in previous videos, that is energy divided by the number of molecules is equal to 3/2 kBT. Now let us understand how this 3/2 kBT comes. In our previous just one video before this, I have discussed the law of equipartition of energy, and which says that every degree of freedom will bring half kBT amount of energy. So because it is having three translational degrees of freedom, it is going to have half kBT for x-axis, plus half kBT for y-axis, plus half kBT for z-axis. So with that you have 3/2 kBTs for a single molecule which is trying to move in the x and y and the z direction. Now let's try to play with this equation now, and we'll land up with gamma very quickly. Now as we know that n, that is the number of moles, so this is number of moles, is equal to number of molecules in a gas, and this is your Avogadro's number. So you can just pause and you can just note it if you think you might forget. Number of moles is number of molecules divided by Avogadro's number. So I can just move this Na on this side, and I get N is equal to N times Na. Now wherever there is a capital N, I can write as small n into capital Na. So wherever there is a capital N, I will write as N times Na. So N times Na, this becomes N times Na. Now move this Na on the other side. So what remains is U upon N, which is called as the kinetic energy per unit mole. Single mole kinetic energy is U by N, and this becomes 3 by 2 Na into Kb into T. So in this equation you just have an Na extra over here. Now we had discussed while we were discussing about ideal gas equation that universal gas constant is nothing but Na into Kb. So this is becoming Na into Kb, and I'll put in place of Na into Kb I'll put single R, so that's a single R. Now just differentiate this with respect to the temperature, because temperature is the variable on the right hand side. So I'll differentiate this with respect to T. So I'll get du by dt, but n is a constant, so that n is thrown outside. So what remains is du by n dt. And on the right hand side, if you see 3, 2 and r are constants, so that constants will be thrown outside. So what remains is dt by dt. Of course 3 by 2 r is outside, and dt by dt is coming out to be as 1. So what remains is 3 by 2 r. And this is 1, we generally don't write that 1. So you get 3 by 2 r. Now du by n dt is nothing but Cv, that is the specific heat at a constant volume. So that is equal to 3 by 2 r. Now in Mayer's equation we had understood that Cp minus Cv for any gas is always a constant, and that is a universal gas constant. So Cp minus Cv, that is specific heat at a constant pressure to specific heat at a constant volume, is equal to R. Just move this Cv on the other side, so it will become minus R will become plus, and then Cv ka value I have already found out as 3 by 2 R, so that is 3 by 2 R comes here, and 2 ones are 2, 2 plus 3 is 5, so I get 5 by 2 R. That becomes our Cp, that is the molar specific heat at a constant volume. Now ratio of specific heat is gamma is equal to Cp by Cv. Cp ka value is 5 by 2 R and Cv ka value is 3 by 2 R. R and R gets cut, 2 and 2 gets cut, and what remains is 5 upon 3. And this gamma is coming out for a monoatomic gas. So it works either ways. So if a gas is monoatomic, then the gamma ka value you can take as 5 by 3. And if the gamma ka value is given to be as 5 by 3 in some numerical, some MCQ, some problem, then you should understand that the gas is a monoatomic gas. So basically this gamma becomes the signature of an monoatomic gas. Okay, so this is all about monoatomic gas. So for gamma ka value 5 by 3, it's a monoatomic gas. Now just make sure that if it is possible for you at your end, then just try to do it by yourself for a diatomic gas, or a polyatomic gas. Now what thing happens is in a diatomic gas, this 3 translational degrees of freedom changes. So this 3 will change, so this 3 will change, and everywhere you have just this 3 changed at every different locations. So 3 will change, so this 5 will change, and you will get a different ratio of a diatomic gas. Okay, anyway, you can give it a try. In case if you are not able to, then I'll be doing it in the subsequent video. Thank you so much for watching the entire video. I hope you are liking it and you would subscribe the channel, and please do comment on how you are finding out my videos, and thank you so much. Bye.